for today finish this supervised topic, this supervised learning chapter, with one other pretty important topic that we will revisit on and off over the next months repeatedly, namely that of architecture. So, right, how does the neural network that we use for these tasks look like? And this is in addition to picking suitable setup and constructing a loss function and setting everything up, a pretty important consideration, and also often a question that you get from people getting into the field. Well, right, what kind of network should I use? What's applicable to my problem? So we'll cover it not in a huge amount of detail, but at least to provide you some starting points. The following slides should give you at least the main issues to consider when choosing an architecture. What I want to focus on here in the context of physics simulations is actually primarily related to what we normally also do in a solver. Right? That is in a way the main content that we want to provide you with in this lecture. If you have a physics simulator and we want to use learning, how do we bring the two together? And also the choice of architecture is actually closely related. So what in a way the crucial consideration to make is what does your data look like? What are we working with? Right, sounds pretty obvious, but there are differences. So the simplest case that we'll also actually use in quite a few examples in the following is if we just have a regular grid. Right, so you have a nice grid structure with regular spacing. That's as nice as it gets, both for a numerical simulator and for a neural network. So if your simulation looks like this, it's actually a good idea to mimic that structure in your neural network. That's also what many classical CNNs and vision-based approaches actually do. So there's a lot of functionality to build on that makes this a very attractive starting point. It is for many simulations not necessarily the best one, because if you're interested in, say, right, a classic example would be a flow around a car or something, we know the car matters. What happens close to the boundary of the car is pretty important. So probably you want to spend more resources in the vicinity on the boundary layer around this car. And then in many practical scenarios, we would go away from the structured regular mesh and do something that actually is, for example, finer near the surface of the car, and right, could be unstructured. Right, you could have all kinds of computational elements in there. Triangles or tetrahedrons in 3D are a common point, but there are all kinds of specialized structures. So main distinction here to make is we have something perfectly regular in the first case and unstructured or fairly unpredictable in the second case. You can see it as a generic graph. This is actually quite commonly used, and we get back to it in a whole section later on. If you don't know anything about the spatial arrangement, right, you just have individual values that you want to work with, a data set that consists of, right, basically disconnected or spatially disconnected quantities, then, right, you basically don't know how they go together. Then there's not much to do on the spatial level. So that's, so in this case, if we don't know the connectivity, so if you have, similar to before, positions, but you don't know exactly which of the positions is connected to which other ones, then it's more a particle nature. So you have individual, right, samples that move around. And I just mentioned already, this the last case, if you have just measurements, right, could be right, also certain sensor data also that you work with, or even in the physics context, it's actually probably rare to have this, but in other settings, you might have, right, preferences of some viewers or users or something abstract that's not fixed to a spatial location. And that is the last case where, right, you actually cannot exploit any spatial arrangement. But that's probably quite rare in the physics setting, so mostly we can, or these three cases should cover a large range of different applications here. And that's basically a regular grid, some unstructured grid, and particles. And depending on what you have in a simulator or in your physics, the network actually can be chosen accordingly. One kind of second dimension that we can consider, independent of the discretization, is how tightly the different quantities you're working with interact spatially. So it's related to what you would call in vision and related topics the receptive field of a network. And it basically, or main consideration here to make is, do the quantities and unknowns we work with interact locally or globally? Right? So if you imagine working with the air in this room, if I do something here in the front, right, if I create some smoke or something happens here in the air, the interaction with the back corner there is actually not that strong. That's largely a local effect here, right? If I blow into the air, not much happens up there. So that's pretty local. Whereas if I would be interested in something that's inherently small and do the same one, then it might affect the whole region I'm interested in. So depending on the scale that we're interested in and the kind of interactions, that makes a big difference. And it's actually closely related to the traditional classification of partial differential equations. Some of you might have come across that. So we can distinguish hyperbolic PDEs, typically related to the order of the terms arising in a PDE. I don't want to go into all the details here, but it's a classic distinction between mostly localized effects such as wave propagation, right? Waves locally traveling in a certain region, and other effects like heat spreading in the long run is something that's potentially global, right? If I make one corner here very hot and wait long enough, then a lot of the heat will actually have spread all over the room, even though it's probably lower at the other end, but this is a potentially very long range or a global effect. That's a classic distinction between hyperbolic and parabolic and elliptic PDEs on the other side. And that actually changes, you probably imagine, but also the kind of things we need to learn, right? If we have something that is very local, like these waves, our network should focus on these local effects. Whereas if we know that we need something like this global propagation of information, then our network should support this. Otherwise, it's in trouble. It's a very difficult task. Yeah, so in a way, not too surprising, but the important reminder here is if we know about a physical model, how to set it up, these classical considerations actually do play a role for physics-based learning as well. Yeah, so what might come to mind here is, well, if we take a fully connected usual neural network, well, it connects everything with everything, right? So that's inherently global, should cover everything, right? You cover all the potentially local interactions and it just connects everything. So globally, global interactions is also no problem. That's true. That's also what you would do in a case where you don't know much about space, but they scale badly. So you remember, right? If you have an MLP of a certain input size and an output size, it's essentially a dense matrix. Right? It connects every quantity with every other one. So if we assume we have something on the order of n as input, similar output, this scales with n squared. And then as n grows, that will be infeasible. And typically also we can't do away with one MLP, but we need to concatenate multiple of them, potentially adjust it to the difficulty of a problem. So that's not a good solution in the general case. What can we do about that? Well, let's start with the local viewpoint. If we know we have these local effects, or we know that they at least play an important role in the system we're studying and the system we'd like to learn, then no matter which discretization or representation you have, whether it's a regular grid or graph or these particles, you can look at basically at stencil-like operations. So from the learning perspective, this is actually equivalent to a convolution, right? A convolution is essentially, or in the continuous setting, you say folds with a certain function. If you discretize that, you have a certain weight for certain sample points. That's very much in line with the local stencil operation. It's basically a local influence region. And that's exactly what these normal convolutions do. That's also exactly what the message passing step on a network, graph network, does. And the same can be applied to particles. This is really with basically a Fowler function around particles. So the stencil-like viewpoint is actually one that directly handles these local inferences, and that's actually super common in CNNs in this regular setting. But the same viewpoint actually holds for these others as well. So whether you call it message passing or you actually call it convolution or stencil, that doesn't matter too much. So we'll, in many examples, look at this regular grid because the convolutions are well supported and quite easy to implement, but it's important to keep in mind also going to the graphs later on, all these ideas carry over. And it's also worth noting that even if you have something like a simple grid, you can actually do quite a bit with that. So down here is actually an example. I hope you can see it here in this swirl. It's a regular grid. You could just display this as a normal image, but it's representing something that is basically wrapping around a sphere and deforming. And if you then look at a simple 3x3 neighborhood here, this is actually covering a non-trivial region, and potentially the same kernel could cover a smaller, more refined part here in the inner domain. So yeah, even the seemingly restrictive regular grid could actually cover quite a range of cases if you set it up correctly. Now, main message here is with these convolution-like operations, these stencils, you can cover the local effects. That's also exactly what classical simulators do. How do we get to the global ones? And there are some different variants. So the main goal here, again, from a learning standpoint, is how do we enlarge the receptive field? How can we go away from these local ones to larger and potentially global ones? And one classic remedy or approach to arrive at global effects is actually the old pooling approach. So on a regular grid, instead of staying on, say, a certain resolution, classically for an image that you're working with, you downsample the image, you make it smaller. That's like a coarsening in multigrid or other approaches. It essentially reduces the number of sample points. Right down here you can see a sketch of that. We're starting with a certain resolution. The details don't matter too much. And then we are reducing by a factor of 2 along both spatial dimensions. That directly reduces to a quarter in 2D. And now if we apply the same 3x3 convolution, because effectively we're representing our data with fewer samples, it covers a larger spatial region, right? That's intuitive. So from an implementation standpoint, it looks like we're just making the data smaller, but think of it as essentially covering a larger spatial region with that convolution. And then if you continue doing this, in this case, one more step is enough. Here, the 3x3 convolution directly covers the whole domain, and the convolutions are actually internally densely connected, right? They let every point in the convolution interact with every other point. So for this example, after 3 steps, we actually have a global influence with this 3x3 convolution. Yes? So the question was about the same convolution. So convolutions are applied to every of these points, right? So also because the data is inherently different on these 3 grids, right? They inherently look coarser or cover different scales. You would learn different convolutions for each of those, and they would be shifted around the whole grid. In practice, it's just the images just show one application of a example 3x3 convolution. But in practice, for most cases, actually, unless you can rely on self-similarity across scales, you probably also want different weights in each of these convolutions. Because of the compression, also good to mention, but you also typically expand the number of features, right? So this dimension typically omit, right? You have a feature dimension in the depth here, and typically because you compress spatially, you grow in terms of these additional features, or you increase the number of degrees of freedom along some orthogonal dimension, same would hold in higher dimensions, so that these convolutions don't lose too much of the information. Yeah, so it's actually a pretty simple and classic trick. You could interpolate smoothness depending on your problem are the different considerations, but even just with the local leaving out data, like an injection operation, you actually get a global effect. It's also directly applicable to graphs. Even if this is unstructured, you can basically do clustering. You can coarsen your graph from something that's very fine to roughly 1/4, and keep on doing this until you arrive at very few computational nodes covering a large part of your domain, or in extreme case, you could even try to go down to a single node to force a global kind of global compression in your representation. For grids, there's one interesting variant that you might come across or might have already come across. Who has heard of these dilated resonance? I mean, okay, good to mention. Then there are so-called dilated convolutions that are popular that actually aim for a similar effect. What they do is, instead of pooling, they basically spread out the points where the convolution's applied. So I think if you look at this picture to the next one, it's very clear. It's a 3x3 convolution, actually, in all of these three settings. We simply spread out the lookup points for the convolution further and further, so by a factor of 1 and then by another factor here. And that way, again, the same 3x3 convolution covers a larger field. It's actually similar to leaving out data. There's a slight difference in that convolutions are applied to every input point. So these convolutions are applied more often than the one on the left-hand side. But both arrive at the goal of basically looking very far. So this convolution now covers a whole large spatial region, and still uses only nine actual points in the convolution. So this is a popular approach in the grid world. You could do the same idea in graphs, but it's non-trivial there. You need to pre-compute how to enlarge these neighborhoods, so it's less common. Probably because it would require so much pre-computation. I haven't seen it. There, the clustering and these hierarchies are actually more commonly used. But especially for regular grids, because it's so simple to do, it's an interesting alternative. One other variant that you might come across that's worth mentioning here are spectral representations. So going to the Fourier domain. And there are, for example, these Fourier neural operators, FNOs, that you might come across. They're motivated from a very different perspective. So they typically come from this operator perspective of transforming infinite dimensional function spaces. So the theory behind it is actually interesting, but potentially also whether all these complications of formulations are actually necessary, I would sometimes question. And in practice, we are in computers actually working with discrete points in discretized settings. So these infinite dimensional function spaces rarely translate into arbitrary amounts of detail and content. In practice, they're actually not too different from normal CNNs, but have some interesting different properties that are worth pointing out. So important point here is don't be scared by this very different viewpoint. In the end, it's actually much like a CNN. The big difference is that they basically perform an FFT. So if you have an input, you transform it into frequency space, right? That's a classic transformation. It's completely invertible, right? We can go back and forth in the discrete setting, even with a finite number of sample points or frequencies. And the main difference now is that we take, for example, 2x2 image from an FFT, so we have a frequency representation, and now in order to change the input, what these FNOs do is they apply an MLP on a certain region of the frequency content. So typically, the very high ones are potentially noisy and more difficult to work with. So the lower frequency modes, the large-scale structures, those are modified with an MLP. So this part indicated in yellow here that changes based on learning, based on some weights for a certain case, and then we do the inverse FFT and get back our spatial data. And you can actually motivate this from this operator perspective. It essentially means we are, with a manual selection, changing a certain frequency range in our input data. And the important bit here is that FFT works with these basis functions, the different cosine terms of different frequencies, and they're actually global. So each of these is just indicated here in the sketch, but they actually have a global support. So by changing one point here, potentially I can change the signal in my whole domain. And as such, these changes here, even if they're only working on a part of the spectrum, actually can change the data everywhere. So FNOs with this frequency viewpoint do actually achieve inherently a global perspective. They can't work with very fine details. So they basically, as a trade-off, lose the capability to work with small-scale features, but give us a global support. It's worth mentioning that it doesn't scale well. Unfortunately, if you go to 3D, this is sketched here a bit, we need to do a 3D FFT. We need to work with a cut-out cube, basically, of these frequencies, and we need a dense connection between these, because they actually, their frequencies. This is not so easy to work with, or blurring over them spatially is tricky. So we get a dense connection, so another square, and for 3D, this gives us a power of 6, and a power of 6 scaling is not great. So this is actually better for normal CNNs. Normal CNNs also scale not that great in terms of the kernel size. So if we have a certain kernel size of k, then also in 2D we actually get that squared. So it's similar to what you get in 2D for these FNOs. The k here can be separate, and I think this actually also should be a 6 here for the k. But the important bit is that these k factors, they deal with potentially localized features that are typically smaller than n, and they're nonetheless applied to all of the sample points. So we have a factor of n squared and n cubed here, but this n cubed is still better than this n to the 6th power for the FNO, unless you make the k too large. But I hope you can at least roughly follow that these convolutions have a better scaling for 3D. In 2D, they're actually similar. It's also quite popular, but if you go to higher dimensions, 3D, or if you even have something 4 or 5 dimensional, then this FNO viewpoint would actually have problems, because we basically need to explicitly deal with this global information as a part of the frequency spectrum with a dense network. So yeah, some interesting considerations to be made here. I think it's good to keep in mind. I do want to basically end here for the architectures. So main considerations are the distinction between local and global features on a grid. For local ones, we have these classic convolutions. ResNets are actually much in line, especially in terms of the receptive field, not much difference. For global interactions, we can either go to these hierarchies, as mentioned before, or FNO gives us, with the frequency perspective, a different global viewpoint of the data, and this kind of distinction carries over to the other discretizations. So the message passing steps for graph nets are in line with the local points, and for graphs we can also look at hierarchies or potentially spectral decompositions for the graphs. A bit less easy to compute. You typically need an SVD or some more involved computation on graphs, but nonetheless this is actually still possible. And on points, the spectral decomposition is a bit messy. So this is not widely known as far as I know, but hierarchies are nonetheless directly applicable in a point setting as well. Right, so the local global switch nicely carries over. One other outlook that I want to give here, we'll potentially come back to that later on, but these transformer architectures, you heard of those in one or other settings, are really popular lately, and in a way also a bit orthogonal to this, providing a global connectivity. I don't want to write graphs. We will actually cover in detail the transformers. I at least want to give as an outlook. So transformers come from ChatGPT and co, more language processing, and it's really a bit of a different viewpoint of how you work with the data. It basically works with a sequence. So instead of now taking an image or something that's connected, these transformers come from basically a long sequence of different pieces. They're typically called tokens. So for example, syllables in a word, typically these individual tokens are pretty high dimensional. So internally, for processing, you already map them to a potentially larger space. For words, you often have these word embeddings, 10,000 dimensional or so. So these individual tokens can be quite large, but then you just have a sequence of these tokens one after the other that you somehow process. And now the main ingredient of transformers is the so-called attention mechanism, and that's actually also what yields the global passing of information. So for transformers, it's typically motivated in terms of exactly these word sequences. So you have different tokens of a sentence, and then you want to find out, maybe a noun in a sentence is closely related to a certain verb that comes at a different place in your sentence. And attention basically gives you this from a certain input. It gives you a certain attention weight. And imagine it like a scaling factor to all other bits in your sequence. And this is happening for every part of the input. So again, it's basically densely connected. So this also, again, scales badly. This is quadratic again. But this is how the attention mechanism at its core works. If you look it up, it's actually typically expressed in terms of three different matrices for these query key and value pairs. So there are three different matrices that you learn and then form first projection and outer product of to get this quadratic matrix. But unfortunately, in practice, the scaling of this attention mechanism here is quadratic in the number of tokens. So there is a chance if you can reduce spatial information into compress it into one token, then you might get away with this for larger inputs, but the number of tokens n here, down here, this attention is n squared. Yes. The first one, I think the Q is typically pre-multiplied with the inputs. So it's more of a additional encoding step, and then the last two form the n square.
Okay,
so
it's
really pre-processing, and there's also softmax in there to turn it into probability for the actual for the weighting. So it's traditionally really thought of as an attention. One part is more important than another one. In practice, you actually just multiply it with the input and add it again. So it's in practice, I think, often used more as a residual update. It's a weighting of the input that is added to itself. Traditionally, it's just called an attention layer. And this is actually where a key component of the transformers and also how they can communicate globally. And by now, actually, if you think about what current large language models can do, they have huge input length. So they must have gigantic resources. The details are a bit out of scope, But the interesting bit is exactly that they actually scale well. In a way, they're actually not, if you look at a certain size, they're actually not that different or not inherently more powerful. The main attractiveness of these transformers is that you can relatively easily make it bigger. And that's where also the current large language models actually profit from. Right, they have billions of weights of degrees of freedom, and the scaling turned out to be crucial there. I think we need to be a bit more careful here in the context of numerical simulations where we actually have alternatives, but nonetheless, the scaling capabilities are actually really attractive of these transformers. There are also tricks to deal with these potentially quadratic and suboptimal scaling of the tension. There are all kinds of tricks by now to at least partially get better scaling properties, and hence I think it's definitely a very interesting architecture to keep in mind and an alternative. So I found it important to mention it here directly in this discussion. We focus for now, just because of the focus on physics models, on CNNs mostly, and then come back to graphs and unstructured meshes in a bit more detail. But transformers are actually applicable to all of these. You can basically encode either for this token, this patchification step, or for encoding these tokens initially, you can either exploit regular spatial information, or you can directly embed more unstructured information from graphs, and potentially points are actually pretty much the same. The connectivity of graphs, I think that's actually a bit of an open topic, how to best encode that, but right, all three representations actually do fit nicely into these transformers, so it's also quite orthogonal and essentially addresses the question of how to encode the global information. Yeah, to finish the architecture also, right, it's not done with attention, so these normalization and an additional processing step, just per token basically, are also important, but right, typically the main workload, the most expensive step is actually this attention in the beginning. So much for an overview of different architectures. So I think essential takeaway point here is this consideration, local versus global, especially if you know kind of what you're dealing with, the physical system is inherently local, then I would recommend, right, don't waste resources on trying to encode global information. Things like FNOs have problems there. So if you have knowledge here, that's good to exploit. Vice versa, if you know you have a large number of long-range effects that play a role, make sure that you have good capabilities for global influences. In practice, many problems will probably have both. So it's also a good idea, or if unsure, to make sure that your architecture can deal with both of these kinds of effects, at least on a reasonable level. And most of the other concepts, actually, right, whether you have regular grids or graphs, or want to apply transformers, is actually relatively orthogonal, and also the following applications of physics models that we'll discuss and apply here actually also pretty agnostic to neural network architectures. It just changes the kinds of inputs or how your inputs are encoded, but right. We will actually typically not, in the following slides, spend too much time or too much detail on what the neural networks look like that we're using with, but more on how to formulate physics constraints. Any questions on that side? No. Excellent. All right. Then let me switch to the next chapter. Yeah, so in this next part, we now finally really want to get started with actual physics, or how to use physical knowledge that we have about the system that we want to work with or learn, how to integrate these. And this is going to be a bit of a larger section of this lecture. So to give you an overview, what we look at here are first loss terms motivated by PDEs or physical models, then extending this to whole simulations, and then I'll also show a few examples. There are some additional considerations to be made for training. I'll come back to that. There are actually quite a few different ways of setting this up, and also there it's worth looking at some examples. So roughly we have kind of 3 subsections here, and today we'll focus on the first one, the loss terms. How do we work with physical models? It's worth repeating at least the basics of a simulator, because that's what we'll be using, as mentioned last week already. The goal is that we can kind of reuse as much as possible that the knowledge that was developed and the methods for working with physical models, typically in the form of differential equations or partial differential equations. And if we have a model that we know is applicable to our case, it will in the following typically be called P with the script font and certain states U. Then this P will be assumed to take a U at different locations P at a certain time T and update it in time, for example. We will actually usually leave out this position, right? So most cases we'll be dealing with spatial data, right, like air in this room, but please keep in mind this U could be the velocity of the air, varies, so it's a function of space. What's potentially more important is it varies over time. So the time indicator with a superscript or a parameter will be kept around more, but actually, many of the ideas would work if we ignore space and just deal with point data, but usually all the ideas and concepts actually do extend to something larger dimensional. And I want to motivate the kind of idea with these loss functions from a fairly abstract perspective first. So if we have a physical model, no matter what this is, we can, in pretty much all cases, reformulate this to just compute a first-order time derivative. So these derivatives will usually be denoted by a subscript. So the ut here means, right, you just take the change of a quantity u over time and formulate it as a combination of different spatial derivatives. Could be any order, right? Could be typically maybe first or second order terms, but we have all kinds of derivatives in space that tell us how to update our quantity u in time. Very basic setting for PDEs, right? PDE, partial differential equation, because right, we're relating space and time derivatives. And if we have this, we can actually apply time stepping schemes. I hope that's familiar with quite a few of you. So if we have a time derivative ut, in this case we can do an Euler step by some step size dt to get an estimate at least of a quantity u at the next time step, but potentially also you could form higher order integrators here, explicit implicit schemes. So this is a pretty generic viewpoint. The important bit is basically we have some function f here that tells us how to combine all these spatial derivatives into a change over time. For some equations like Navier-Stokes, where we have basically potentially multiple equations and in the compressible setting a constraint like this divergence freeness, it might not be so easy, but even there, with the right techniques, you can actually break this down into updates and ultimately changes over time. We actually look at this in a bit more later. So now we want to use this physical model in terms of the f in our loss formulation, in the neural network training. And the generic way to do this is now to say, well, we have a neural network that produces a solution. So before we looked at time stepping, so if we say we're interested in a solution u at time t plus delta t, this would be equivalent to the y's that we had before, right? And maybe we have a ground truth value here, but right, this is our basic network training. So our network now should take an input, maybe a state at time u, and produce the next one as y, right? So basically, just to connect it with our previous notation, we have a network that produces the solution at a certain time t plus one step. And now we can bring in these PDEs by evaluating these different spatial derivatives for the time change f at this location. So if we use our network to compute a u, we can actually form a residual very easily for this Euler step by saying, well, we have our state at the next time step. We had the previous one, right? That's what we started with. That's also what the network got. And now we have this f that computes all these derivatives, and all these together, right? That was the time step for an Euler step. So if we basically subtract this from the next time step and the original one, then we should have 0. Or vice versa, basically, right? These two together should be equal to the next time step. And that's a residual equation. So we know that if our solution is correct under this physical model, this actually should be 0. Does it make sense for everyone? Right, this is actually, if you think about it, directly something you could potentially train with. Right now we have an expression. We know if our solution is correct for the physics, this should be 0. So yeah, we can actually directly train this into a learning goal. We say we take this expression. We know our f, as still highlighted up here, produces the next time step. So if we compute this whole thing for f, so we take f minus our time derivative times time step minus the previous state, then all this should be 0. If it's not 0, there's something wrong. So we minimize the squared error and try to bring this down to 0 to make sure that whatever our f does, our learned function actually satisfies these physical constraints. And that's already the main idea behind these residual training processes. That, of course, leaves a lot of questions unanswered. What does this f look like and how to implement this in practice? But that's the main idea. And we have a physical model. We formulate a residual that should be 0 if the physics are satisfied. And then we basically just minimize this. Nice side effect of this is that in here, we now we actually don't have these y star anymore. We actually seemingly don't need any ground truth. That comes from the fact that we're basically computing the ground truth on the fly. Right? So we know that the ground truth for this residual is actually 0. So right, that's trivial. We don't need to store this, but our target, our learning target for these quantities throughout is 0. And the other parts, like these quantities or this time derivative here, those are computed on the fly, right? So depending on how complicated it is, it might actually be quite costly to compute this f. More on that later. But yeah, in this form, we actually don't need to pre-compute much. We just rely or train our network here to satisfy whatever is encoded in this residual via f. Yeah, so if we plug this into neural network training, in practice, what you will see is a formulation similar to this one. So we have this residual r from the previous slide. You can really directly put this in a loss. In practice, what is usually done is to still include some ground truth. That comes from the fact that these residuals are actually tricky to train with, because they kind of just relate different parts of the data. They are highly ill-conditioned in practice. And to at least reduce the problems you get there, it's a good idea in many situations to rely on some ground truth data, some direct targets, and compute first a kind of supervised loss term here with a certain factor alpha 0, and then this residual term. In learning, it's quite neat, right? We can add up all these terms. Our learning will minimize anything that we put into the loss. And typically, well, they should be somewhat matched, but if our training is successful and has enough capabilities, eventually all of these terms will progress to 0 as much as possible with a given network. And right, we can let the network basically figure out how to best combine these two aspects here. So yeah, these alpha 0 and alpha 1 factors are typically necessary unless you use better optimizers to make sure that one of these terms is not orders of magnitude larger than the other one, or one of them is too small and ignored in practice. But the main idea here is that if we put this into loss, we can rely on backpropagation through all of this. So we basically know that here the f can be backpropagated through. That's by construction, right? We can always get to the weights in training. And we need to make sure that from this R, that internally also used the evaluated quantities here, we can relate whatever was calculated back to the parameters of a network, the theta. And then we get a combined update, a gradient from all of these quantities. It's typically also accumulated over multiple sample points. But all of this together gives us a gradient with respect to these theta values with which we can train the network. So more on what this R looks like in a moment. That's just to give the general idea here of training with these physics residuals. Yes, there was a question. Why is it difficult to train with the residuals? We will come to that in a moment. I will give some examples. Intuitively, the pre-computed data gives you a kind of global target. No matter what your network does, the network will get a gradient that it needs to go exactly there. These residuals are typically more relative. Like a gradient, you take the difference of two quantities of the network that might miss a global offset or other parts of the direction. So by now there is actually some theory on that. What you typically can analyze here is the second derivative, the Hessian of the update, and the Hessian you get from these residual terms is very ill-conditioned. So there's really a kind of theoretical foundation for why this is problematic. The intuition is that it's a relative update that can go wrong in practice. So this term by itself, these residuals are potentially difficult to train with. Yes? Also a good point. So why do we need this at all, right? If we have the ground truth data, can we just directly train with it? Yes. The attractiveness of this comes from being able to use less. So, for example, what you can sometimes do here is you can just use parts of the training data and let the residual fill in other parts, or really just work with less data. So you can have fewer samples and let the residual make sure that in between the samples, or maybe even a bit around it, the network learns how to deal with or how to produce the right solutions. Avoiding overfitting, it does in practice help, yes. If you have a very small training data set and you try to fit a large network, right, it would potentially overfit. And then if you have residual terms, that would prevent the network from overfitting to just these points. And help in the in-betweens. Right. Yes. How to compute these weighting terms? There's no, it depends completely on your setup. There's no ground truth value. What I can recommend in practice is you can, if you have a new setting, you can actually see what kind of gradients you get from each of these terms. So you can look at the gradients for your network that result from this first part and the gradients you get from the second part. And in practice, they should, on average, be on a similar level. So you can gather some statistics of what your gradients look like, and then usually it's good to adjust these factors accordingly. But unfortunately, right, this, like so often in this context, there's no global ground truth. Yeah, so the visual outline here is to bring back these pictures we had before, right? So this progression, we have an input of a network, our x, we compute a y, and now instead of directly computing only the supervised loss, right? So often there is the supervised loss, as mentioned before, it does help. We want to keep it around, but now we go further, we compute some derivatives of this output, and now we have a target of 0, right? That's kind of this trivial residual target that we actually don't need to store. But based on these two components, the residual loss, we backpropagate through the residual, then optionally evaluate the direct loss for output and propagate that to the network. Right, so it's been a bit abstract. I now want to provide some specific examples of how to put that to use. So before coming to that, as a quick side note, we are looking at this time stepping here. Potentially, you can apply similar ideas to steady state solvers. They also internally have a time or an update loop that is not really a time, but right, a kind of abstract update, but effectively keeps on updating a solution starting from 0. And these ideas are typically quite similarly applicable to these updates of the virtual state of a steady state solver. So just as an outlook, this is not completely beyond the scope here, but for simplicity, we'll keep on looking at this time stepping question. All right, first example of how to put that to practice. So one variant to employ this residual-based training is to use a grid-based discretization. For simplicity, we use a regular grid as shown here on the right-hand side. So our U are basically different spatial locations where we have the solutions, dense regular array, and now we can compute this residual R on our regular grid, right? So we could, for example, now for some value of our U here, we could compute a central difference or higher order differences, or right, any differential operator from classical numerical methods to compute gradients of any order. And if you think about it, what a central difference here does is basically, right, we would basically take the one value minus the other one divided by the step size or so. But this is, as mentioned before, this is very close to a convolution. So this is actually pretty easy to derive, or you could implement this with a convolutional operation in a neural network setting. And if we have such a setup, computing the gradient of this would be trivial. But if you set up a convolution in PyTorch or so that basically has a weight of one for one neighbor, then a -1 for the other one, right, and provides a scaling of 1/2 afterwards for the step of 2 for a central difference, then you could directly backpropagate through this, because TensorFlow would provide you with a gradient with the derivative of this convolution operation. So the main idea is that you actually formulate this residual in terms of convolutions or basic operations that are differentiable, so that we can get for our residual a derivative or the Jacobian of r with respect to u. And because our network produced the u, we can then rely on backpropagation to take that gradient from our u further into our network and eventually turn it into an update of the parameters of the network. How does that look like in practice? Well, to pick an example from the fluids context, if we look at this second part of Navier-Stokes, this continuity equation, basically encoding divergence freeness. I hope some of you remember that. If we basically have some flow field u, some motions, and we compute this, then basically that tells us the motion does not compress or expand. So I do have an illustration for that in a moment, but this is basically a divergence freeness constraint if we have a vector valued u and treat it as a motion. So that's a fairly simple and basic physical constraint that was also used in a variety of examples before. Now, to enforce that constraint, what you do in practice is you say, well, I have a u, I compute the gradient of a scalar field P, typically that's instantaneous pressure, here this gradient of P, and this should be divergence free. So we take the divergence of all of this, which would then give us a squared one here and a divergence here, and then we bring the square term put u on the other side and bring the square term over, so resolve for P, then we get this expression. So details don't matter too much. I hope you trust me. This is a pretty classic operation. So you can basically compute a P such that it makes these motions encoded in u divergence free. That's a very classic decomposition. Helmholtz-Hodge might have come across this. So in a way, a pretty fundamental operation. And the nice thing about it is it's fairly well known and gives us a constraint for the motions that are encoded in this u. So potentially an interesting learning target. And what we can now take as a task in practice, because this here is actually not so easy to compute, we can let a network F we can try to let a network predict these pressure functions to make our motion divergence free. That's actually typically a fairly complicated and costly step in a normal solver. Yes? Here, this now there's a -2. This is basically the inverse of the Laplace operator. So nabla squared. If you invert it, it's actually typically not directly invertible, but in practice, that is what these Helmholtz-Hodge solvers actually do compute numerically. If you're interested, I can point you to some examples of that, or actually the learning problem we deal with in a moment actually does, in a way, provide that. But yeah, mathematically, just inverting or taking this as a matrix and inverting it is not trivial, or even the Laplacian, but with a numerical solver, that's effectively what you get in the solve. So what we now can do in terms of these physics residuals is we can train a network that is trained with the following expression. It does look a bit messy here, but it's actually in the end simpler than it looks here. So we're starting with some input u. Here, input meaning u of 0 times epsilon 0. We're just going from 0 to 1. And this u minus the gradient of the of whatever our f generates, that should be divergence free. So the divergence of all this should be equal to 0. So this is something we want to minimize. And the network in turn actually works or receives the original motion from which to compute this. Right, so from our notation up here, this is actually this P, this pressure function. And right, this whole term is the gradient of this pressure, so the network should provide some values that make our U divergence free. And although it looks a bit unwieldy here on paper, it's actually relatively easy to implement. And this is exactly implementing the construction I gave before. Here we now have a loss function that we minimize. This divergence freeness should be preserved for basically any U that our network gets. So we can train this basically by just giving the U, or providing random U's to our network and letting it minimize this expression. Right. This actually has to hold at all times, so we can focus on just going from one input to one output. In practice, you could say, well, we have different time steps here, but this actually doesn't matter. And also, to give a bit of intuition, typically the way this is implemented is on a staggered grid. So we have different velocity components on the sides of a cell. And then you can implement the divergence operator, so the nabla dot, by just looking at the difference of these U and V components for one cell. Intuitively, this should all add up to 0. Basically, as much as flows into one of these cells, that much has to flow out. That's essentially what you're computing with these finite differences. So it's quite simple to compute that. And for these values of P, what comes out of a network, if we imagine that this is stored here at the center, then a similar difference along X and Y actually gives us a gradient. So all that we need to compute this is essentially one cell, and then looking at the neighboring values of the P and the U around it. So it's a relatively simple operation, can be computed quite efficiently with something like a convolution. And this is also actually what has been done, which is why I bring up this example in a classic paper from 2018 by Thompson et al. And you can find an example of also here in this physics-based deep learning website. So let me quickly pull that up here. So yeah, if you follow the Colab links on the website here, my cursor, this one here. If you're online, you can directly run this in a browser potentially and also modify it. And the implementation is actually pretty easy. So this uses this 5-flow library, which comes with a few functions. So for example, to implement a UNet, right, this would normally take a few more lines with pooling and different convolutional layers. Not too much of a point here. So it directly gives you a network. And then the interesting bit is this one. So there's a bit of setup for the different grids to make sure that, in this case, this 5-flow solver understands the inputs. But the most important bit is really the loss. So this is the loss function here. All it does is compute, it gets an input V. Okay, we call it U. Here it's called V, but it's the same. That it computes the divergence of that, exactly this nabla dot from the previous slide, and minimizes this divergence in terms of an L2. Okay, to be correct, we put a factor of 2 here for the derivative, but actually it doesn't matter too much. Right? This is primarily there to just add up all the values from all the cells. So this is a per cell divergence for each cell in your grid. Then you add it all up and say, well, all of this should be 0. And every cell in our input should be divergence free. And this is what's minimized with this loss function. And that's now also all that's necessary to train a network. So here in 5 there's a update weights function that simplifies the step a bit, but essentially what it does is it takes a range of random inputs here, puts them into a batch, and then tells the optimizer to update the network with this loss function for the given input. So it's using the right functions. So here we have actually these gradients and the divergence ready, but it really doesn't do much more than what I just explained, setting up convolutions to basically combine these terms. And then we can train this very easily. And feel free to run this in practice. This does actually work quite nicely. So here's an example output. Here's an initial random velocity field with the divergence, so you can see per cell. So here's, for example, a cell that's pretty bad with a divergence of 4. And after applying this correction from the network, you can actually see there's some residual left, right? There's some fluctuations around 0, but this greenish color is the 0 level here. The kind of classic, more expensive solver that directly approximates this inverse is still better. It's closer to 0 here, but if you would train the network longer or potentially train larger networks, you could also get this down more. The network basically can, in this case, in one step, produce such a pressure function that's very close to the desired one and gives the divergence-free output. So if you're interested, feel free to give this a try at Colab. Yeah. Back to the slides. I've mentioned this is just one variant. We'll come back to that in a moment. I hope you believe me, this works. If we formulate these residuals in this way, we can actually train basically without data. And this example also does not use these supervised terms that were mentioned before. In this case, it's actually enough to purely use these residual terms. That comes from the fact that here, one input is actually the whole grid. Right? It's a whole set of values, and the network gets a gradient, an update for a whole set of different inputs as a whole grid. So this is a relatively stable setup that performs well, even if we're only working with this residual formulation. Right, so in this case, we actually need to compute all these operators. It's non-trivial, but in this case, fairly cheap. And we don't need a pre-computed data set. If you look at the example, it actually pre-computes the inputs just to have a kind of data set to loop over, but it's really just inputs. The targets are really evaluated with this residual on the fly. And right, the nice thing here is that this actually gives you a per data point update, so it does not have this underside averaging that I also mentioned last week. To look ahead to the next approach that I also want to describe, it's not adaptive. It actually relies on these operators being computed properly, and potentially it's actually slower than pre-computing data. But we do need to compute all these operators. In this case, it's pretty cheap, but we do need to compute the gradient and the divergence. In other cases, this might add up. We need it both forward and backward. So it is potentially slower than a supervised training. Right? So basically, the forward and backward pass through this R adds to the cost of training. This needs to be done for every sample in our batch, for every training update. Another variant of these loss functions that I want to mention is if you use an MLP, a fully connected network, to represent the solution, and then directly compute derivatives of that network. So that's actually what you often find as physics-informed neural network in the literature. And by now, there are also quite a few papers dealing with these approaches. The basic setup is the same. We're training with these residuals. The main difference, it comes in how to compute the gradients. So now we basically have an explicit f that takes the position in addition to the other parameters, some global parameters and whatever might be necessary to form the problem. And what you can now do is you can rely on, again, the functionality of a neural network API to provide gradients for basically any parameter that you put in. So if you let PyTorch or something compute the gradient of your f, so this notation, it would basically be the derivative of our f with respect to these p's, which you can kind of hide as part of the x, but if you provide a gradient for x, you also get actually the ones for p in this notation. This is something that you can get relatively easily in, say, PyTorch or any neural network API. And if you have one, you could potentially do the same thing again to get a second derivative. So you can actually use the basic functionality to compute any derivative you might need and then piece together your physics model based on these derivatives. So similar to before, you could compute a divergence by basically telling PyTorch, give me the spatial derivatives of f and put them together. Or you could form other PDE equations with this. And this is what's quite popular in this pin area. The main difference now is that really the network itself encodes a solution. So we don't have a grid or so anymore. Before we had this grid with the values of u, like an image. And now to get a certain velocity at a certain point, we would basically need to call f of that location. Then we'll get a value of u. The good thing is we can basically rely on the API around it to compute a derivative in that point by just telling the API, give me a derivative of this network with respect to the input location. It changes the picture a bit in that now, to indicate that step, we have all kinds of derivatives of our f that are computed to form the residual, these r values. So it was kind of hidden in the previous step and combined in just this green arrow here. The main difference is that now these derivatives really come from the f itself. And this has some interesting implications. So there's also an example I want to show here. For a different case, the physics model, or the implementation of the physical model, is quite simple. So here is the basic Burger's equation, so a bit similar to before. Normally you would have the time derivative here just given in terms of, we have a function that we, in this case, u is actually our function, just the gradient of that, the derivative with respect to t is the change in time. The one with respect to x is this first spatial derivative. And then here we just take this x gradient and do the same thing again. Take another derivative to get the second derivative. And then Burger's equation is actually very easy then written as the time derivative plus u times the spatial derivative, first spatial derivative, minus some diffusion term here chosen as this constant times the second derivative. So these few steps where this typically comes from the neural network API are all that's necessary to implement the whole physical model. And again, taken together, this is now our physics residual. This is for the time update. We can again train by just saying, well, minimize this bit. This should hold for all points. So basically, no matter what x we put in, also no matter what t, for all points in our domain, this should hold. And also, if you rely a bit on training around it, this is quite easy to train. Well, it's a lot of plotting going on here, but the basic organization steps are really just, in this case, there's still a TensorFlow implementation, so handling these different sessions. But if you run your neural network on a batch of inputs and repeatedly do this for different steps, this is the basic network training. And from that, you can also turn a relatively random field into something that that largely follows the physics encoded in this model. I can also recommend to try this out if you're interested. The main difference here that I want to mention is, this is essentially implementing the same idea. The derivatives now come out of the network, seemingly saves some work on the implementation side. Unfortunately, also has some disadvantages. So for this, we typically need fully connected neural networks because we really directly need to be able to derive the network with respect to space. This can be potentially slow. Usually the first derivative is okay. Higher order ones can be tricky unless you have workarounds. And also these kinds of loss functions now actually suffer much more from this ill-conditioned nature. Because typically we kind of need to query the network locally for each of these points. These derivatives are evaluated locally for certain input points. And that typically really leads to very problematic convergence of the networks. And also, it basically relies a bit on what you currently learned to evaluate the different quantities. So you basically, in the initial stages, especially taking derivatives of a somewhat random function, and you're trying to optimize from that. So also intuitively, in these settings, it's usually highly recommended or necessary to have these additional supervised points. Otherwise, this causes a lot of problems in terms of convergence. So to put this a bit side by side, right, these two variants. For the first variant we discussed, you basically rely on this regular grid and then implement your finite differences with a manual stencil. You can see this both as a pro or con. It's in a way more work. On the other hand, it actually lets you use a good discretization and knowledge of what makes sense for a certain problem to compute this accurately. The second kind, these pin approaches with MLPs, directly uses a deep learning framework, but it's at least much more difficult to use knowledge about your problem in that setting. And also, if you look at what you can, despite many years of research, actually get out of these second approaches, it's really problematic, even for very simple 2D plus time problems or so. It's extremely difficult to get these to converge. The intuition is a bit that these localized updates really propagate very badly. So in the first case, we evaluate the whole grid and get a kind of nice update for the whole structure and all parts of our network. In the second case, we have more localized, potentially very ill-conditioned updates that might only go through parts of our network. And that makes it very difficult in practice to learn any larger or non-trivial solution spaces with the second approach. So my recommendation, if you actually want to apply this to real-world problems, more complicated ones, I would strongly recommend the first kind. The second kind is nonetheless an interesting alternative and also an easy starting point, and there's still active research, so maybe this will improve at some point, but for practical cases, I would really not recommend this. This actually summarizes this argumentation. So in the first kind, we really have updates that look at the whole network and provide gradients for the whole network, whereas in the second case, these are much more localized and badly influence convergence. All right. To summarize on a higher level, we've made a first step today using a physical model. Right, so we had these residual functions, these R's, depending on your problem. Right, we had Second-Burgers example, divergence freeness, but it could potentially be anything, so it's great. Now we have a first step of using some physics in our learning. You might have noticed already it's basically a soft constraint. We're minimizing NL2 loss. So far, I've not commented on right, how far this can be expected to go down. And in general, right, you actually cannot rely on this really being zero, on the physics really being fulfilled. So that's an open question. There are basically no guarantees here. And we are restricted to these terms in the loss. So that's something that we will come back to in the next weeks in more detail. Nonetheless, it's still an ongoing field. So if you're interested, a couple of interesting follow-up papers, or I also recommend to try some of the code examples online. But yeah, looking ahead, what we'll cover in more detail in the next week is how can we use more of the physical knowledge and not be restricted to the loss terms. All right, thanks so far. See you next week.